I do want you to see this full screen here for a second. So um, we are going to derive the model for logistics growth. You don't really need to know how to derive it. It's not nearly as simple as deriving the exponential growth one. That one took us a minute or two. Deriving this model takes us a good chunk of time, but there's a lot of good math in it and it helps you retain it. So primarily, I want you to be able to understand the graphical parts of it and to use the models. So logistics growth is a little different. I screenshot this off the internet down here just so I want you to look at these two models down here. They are going to be different than what I give you. You could Google logistics growth and you'll see different models with different variables. So I don't want you really dependent upon the models that I give you. I want you to understand what the variables mean, understand that they can be called different things and still mean the same thing. So you'll notice it looks kind of like alphabet soup up here with all the variables going on, and I don't want you to focus too much on what they're named. I want you to know what they do. For example, this L right here, I have chosen to use L2. Also, I mean not like L number 2, but L also. But in other texts, I actually think in our text they call it capital M. Doesn't matter, it represents the same thing. Some books they call it capital C. That's my least favorite because even though it's the carrying capacity and those start with C's, C's Carl and we don't want to have to call him something else. So I am going to choose L for that, but I won't have a B here in my model. But I'll have something there. And so I just want you to be careful about getting locked into variables. It's going to be the process and understanding the graphical part of logistics growth. So having said that, let's go into your notes and I'll tell you what it looks like and how it works. It says not much on the AP. I could actually get you successful on the AP questions in about 10 minutes. But I want to do more with it than that because it's actually really good math. I'm waiting for my thing to pop up here. Where did it go? All right, so it says with exponential growth, the rate of change is directly proportional to the amount present. We know that. We've had it a bunch of times that rate of change of some quantity with respect to time is directly proportional to that quantity. I'm calling it Y. It can be called anything that's growing. We've been doing that for a while. And we said that you can memorize what always happens with that. We can do that. We have a model for memorizing the logistics one too after we derive it. But we said that always means that your amount after time t can be the start amount e to the kt. And remember, I call that y sub 0. Usually it's called capital C. Doesn't really matter. You just need to understand it's a start amount. We've been doing that for a lot. That growth, though, continues fast and it continues forever. Right? And as the amount grows, the growth rate grows and vice versa. But usually in real life situations, that's actually not what happens because there's usually a limiting factor that causes the growth to slow down. It's usually something in the ecosystem like space, or food supply, or resources, something like that. So the best example for me to honestly use is like lice. If Mackenzie has 2 little nits on her head, right? They will grow very quickly and boom, boom, pretty soon we're like, gross, we can see them crawling all over, right? But at some point that's going to slow down because her ecosystem, which is her head full of hair, can only support so much. I mean, she's going to be itchy and it's going to be bothering her, but the growth rate will slow down. Does that make sense? Until it expands its ecosystem. So until they hop on over to her head, I mean, there's only so fast they can be growing. And they'll grow fast at first, right? And a lot of things grow that way. So they grow fast at first, but then there's something that limits it. That the limit up at the top gets a name. This point in terms of real world problems is actually the most important one because that's when it's growing the fastest. So if I was in economics, I'd always be in search of that point for money growing or anything growing in the market system upon a logistics curve because that's when it's growing the fastest. That's the sweet spot if I want to have the most growth going on and catch it before it slows. So that's a big point for us right there. Now, back up to here. It says that point right there is actually the inflection point of the graph. So you're going to see me later doing some stuff with a second derivative because I'm going to want to know where that point is. So right, inflection point. So just a generic graph real quickly. So this starts at y sub 0. We normally don't consider this stuff over here because we don't go back in time. So normally we're going to start there. We grow rapidly for a while. Something causes our growth to slow down, but we're still growing just at a slower rate. Are you okay with that? Then this guy up here, I'm going to call it L. I also put a C on there because that's also common. But this is called the carrying capacity. Go ahead and write that. Carrying capacity. It is the maximum amount that can be supported, and we will never go beyond that. We will call that L. However, in calculus terms, this is really what the L is. This L up here, and the reason I like L is it's a limit. Okay, where am I sending time in this scenario? To infinity, yeah. This is really a limit as t approaches infinity of whatever's growing. In this case, it's y, but when we start doing the real world problems, it might be bacteria, it might be B of t or W of t or M of t. I think there's a moose one, whatever. When they ask you to find this limit, they're actually code language or notational fluency is what they call it for finding the carrying capacity. How you find it's very easy. You just have to understand what they're asking you for. So when they ask you for that limit, they're saying what's the carrying capacity. This point right here is going to be very important for us as well. We're going to discuss that later. So it says we call the limit the carrying capacity. So go ahead and write that. You can see why some books or some teachers would call it C, but you're going to see why when I derive the model, I'm going to choose not to. All right. So it says different models use different variables. I've seen A, probably for greatest amount, M, probably for maximum, C, probably for carrying capacity. Those all seem the most realistic. Why again am I choosing L? For carrying capacity. Because it's a what? Limit, and that's how College Board phrases it. So I'm choosing the one that will be most beneficial to you. I actually, at the same time, I like it the most. So it says with the logistics model, it's a little different. So for exponential growth, it just keeps growing, and the more I have, the more it grows, the more I have, the more it grows. But for logistics, it's actually not dependent upon just the amount there. For example, the lice. The rate that it's growing isn't only dependent upon how much lice she has on her head. Wouldn't you agree? It actually depends on how much space is left there, right? Because as her head fills up, they're actually getting condensed in there. There's less room for it to grow, all that kind of stuff. So in terms of the model, without this stuff here, that's exponential, directly proportional to the amount present. This little thing right here is the difference between what? What's L stand for? Carrying capacity and the amount there. That's actually how much space is left, kind of visually. And if there's a lot of space left for it to grow, won't it grow faster? Let's talk about a rumor. We talked about that before, but if I were to tell you something juicy, right, and let's suppose we don't have cell phones, so it's basically contained to this building because we see nobody else, right? I tell you something juicy, you tell these guys. They go to lunch, they say it at the table. The tables go to the class, their next class, they say it to the whole class. But eventually, right, you're going to be telling people, and what are they going to say? I already heard it, okay? But the more people who haven't heard it make the rumor go faster, the difference between the number of people in this building, let's say 2,000, and how many have already heard it, let's say only 100 heard it, that's going to increase my growth rate for a while. Doesn't that make sense? Because there's so many people who haven't heard it yet. But at some point, that difference is going to condense, and there's only going to be like 3 people out there who haven't heard the rumor yet. The odds of you stumbling upon them in the hallway is pretty small, right? So this right here, when you're trying to remember the models so that you don't, yes, we can give her name and call her Kylie because she looks like Kylie, right? But if I go change this to R for rumor, then we have to call it Ryler. You know what I mean? So don't be variable dependent, especially when you're remembering acronyms. Think of the concept. It's directly proportional to how much lice she currently has on her head and the space left for it to grow. That's really what that is. Will Kylie be helpful for you when you're trying to remember the model? Yes. As long as you replace the Y's with what? Whatever variable we're working with. If they're moose, we'll call it right? But so don't be variable dependent. And also make sure you understand exactly what our variables are standing for. Y is our number of things at any time t. And I said number of things because that's going to change. L is always the carrying capacity, the most that I can support. K is what it's always been, the constant of proportionality. So my next task becomes, okay, I know the Diffie Q. I don't want to know that. I want to solve it. And that's a big task today. And I could skip this, but I'm not going to because some of you will understand it. All right, if you don't, you're just going to nod and smile. Okay, so we're going to do a big derivation here. Rewrite it right here. The rate that y is changing over time is directly proportional to how much is present at the time and the space left for it to grow. Did you see how I did not say a variable? Did you hear that? I'm going to repeat what I just said. The rate that y is growing over time is directly proportional to the amount there right now and the space left for it to grow. That's logistics growth. But I don't want to know the rate of change. I'm going to chart that. I'm going to figure out how fast it's growing, right? So I really want to know how much is there at any given time or how long it takes for there to be a certain amount. Just like we did with exponential growth. I want to figure out what's going on. How do we always figure out what the solution is? Separate, integrate, but there's twists to this one that let's see if some of you can get over. So when I separate, I want to keep my dependent variable on the left and all things involving it, which would become 1 over y times L minus y. That's separation of the y's. K is some constant yet to be determined, and dt goes over here. The right looks super familiar. By the way, I put the answer down on the bottom because I want you to watch it evolve. How in the world are we going to take that and get y equals L over 1 plus c e to the negative LKT? How in the world, right? It'll happen. The first key part comes from the next step, which is to integrate it. And then we're going to get stuck for a bit. And I'm going to try to help you. All right? We will integrate this guy. The right-hand side, we've integrated a ton. It is what it's always been. What is it? KT plus C. That's why I didn't choose C for carrying capacity, because then I'd have to say KT plus some variable we're not used to using for the constant of integration. So because I've chose not to use it, I'm okay by having him be our normal Carl. This is where I am right now stuck, and I don't want you to blurt or anything. But when you are integrating, I would never ask you or to expect you to integrate anything you don't know how to integrate. Agreed? So I've given you tools, not a whole lot. I think we have maybe 6 ways to integrate. And what's probably bugging us right now is the y's because we're used to x's and the l's because we don't know what it is. So I'm going to make it a fake 10 so you can at least get its format in something you're used to seeing. Okay, I could have put that on the last test because it's a technique of integration that helps me solve that. So here's how I run through them. And once I hit it, pop up your hand. Who's the first one? I always try. Okay, so I look at that, and is it U sub? And that's where you go crap. Okay, when it's not U sub, it's something else I've taught you how to do. Correct? So we think of other things. Inverse trig. Lord, no. Right? By parts. No. I don't have incompatible functions. So it feels like I'm running out of options. What is it though? It's partial decomp. Yeah, it is. It's a product of linear factors, non-repeating on the bottom. I just have to remember how I use it. So go back over here and we'll see if we can figure out how it works. I need to decompose this guy. So it's a good review of a lot of processes today, actually. There's a lot of our other math in this math. So somehow I'm going to decompose that into something over one of its factors plus something else over the other. When we did partial decomp, what did I put on the top of those fractions? An A and a B. You could choose C and D. Again, don't be variable dependent. It just needs to be constants that you haven't already chosen. So you can't choose L and K, but A and B is the most reasonable, and I have not used them yet. Do I even have a number on my paper? Only the 10, and that wasn't even meant to be there. So that's what somebody said, today is difficult, I heard. It kind of is because it's theory. Right? So let's go over here. Do you remember what we do on this one to figure out what the A and the B are? I picture cross multiplying, or I multiply the entire thing through by y times L minus y, and it goes. But either way, this 1 came from the crisscross. The bottom's the applesauce. So it'd be a times L minus y, and the L bugs us, maybe. But it doesn't matter. My process never changes. Whether I'm doing a proof or an easy problem or a difficult problem, at this juncture, what did we do on the last test? Because everyone got it right. There was no one who decomposed wrong. What did I say to do here? Strategically choose X. Well, you have to strategically choose what? Y. Knowing that Y is the independent variable, not L. L is actually a constant, really, right? What does it represent again? The carrying capacity for this situation. Okay, so whatever the carrying capacity is, Y, if I strategically choose it, could equal what? L is one choice, or Y, if I strategically choose it, could be 0. When I put in an L, right, that would wipe that out, and I'd get BY equals 1. Right, if I let Y equal L. What's my goal, though? Again, it's variables everywhere. Who am I trying to find? Oh, sorry, that's BL. Sorry. Sorry. I'm letting Y equal L, and I didn't replace it. I've got to erase real quick. So when I let Y equal L, I get a 1 equals B times L. Don't forget, who am I trying to find? A and B. So what's B? Okay, that's whatever the carrying capacity was. In every problem, that would have been a 1 over L. Again, the proofs cover all scenarios. That's why there's variables everywhere. Next step, when Y is equal to 0, I would get a 0 here. This would go, so I get A times L equals 1. So what's A? Also 1 over there, L. That's kind of nice. So now it's decomposed back over here as 1 over L over Y plus 1 over L minus Y, and I'll slow down, dy. Hopefully you're not nodding and smiling yet. They were really getting it in my other class. I was impressed. It was kind of nice. The next step, it's all process. No matter what, 1 over L is a constant, and when we integrate, what do we do with constants? Let's do that, okay? Because we want to clean up our integrand there, so let's get the 1 over L, whatever it is. Let's pull it out because it's legal. Now I have a nice antiderivative plus something with a not as nice antiderivative, but very doable. Katie plus C is always just hanging along. All right. Are you good so far, Noah? Now take a look. In this scenario, don't lose track, what am I trying to solve for? So let's get the 1 over L out of there before we try to, how am I going to get 1 over L out of there? Okay, multiply by L. Now look down at the answer. Do you see how that LKT and that exponent is starting to form? Do you see it? It says a negative LKT, but that'll come. I have a 1 over Y plus 1 over L minus Y dy will equal LKT plus C. Why is Carl still Carl? Because it's still a constant, so I don't need to, I'm good. All right, well, it's getting there. Now what? Integrate. That's why we decomposed it, so we could get it in a form that we can integrate it in, right, Molly? So what's the antiderivative of 1 over Y? That's a no-brainer, right? What is it? ln y, and I don't need the absolute value bars because this is a population, and populations will not be negative. They don't implode and go negative people or negative bacteria or whatever. So I can get rid of that absolute value just with my common sense. Tell me why I can get rid of the absolute value on that one. Not because I feel like it, but why do I know L minus Y won't go negative? L's the maximum it could ever be, right? So that, again, I don't just drop them because I feel like it. I drop them because I have good reason to. All right, there we go. Now, at this point is where some people get stuck because when you exponentiate, it has to be the log of a single quantity, and it has to be a naked log, like not a negative ln or a 3ln or an ln plus an ln. It has to be ln stuff. Yes. It is. Thank you. Thank you. Thank you. It totally is. Thank you. I forgot the fraction correction, and it totally will mess up the rest of the problem. So thank you for not letting that go. So I think I would have caught it in the next step, though, because what do I need to do with my logs? Being that I just did it second hour, and something very different would have happened right now. What do I need to do? Divide, yeah, to exponentiate, I need natural log of 1 chunk. And again, I'm going to repeat that, not negative. Some of you leave the negative when you try to exponentiate if you have one, or you leave a 4. That has to get out of the way. So this would be y over L minus y, all right, is equal to LKT plus C. All right, that was a good move, right? Now what? Now I exponentiate. All right, I'm just going to do it right built in here, kind of illegal, but all right. So I'm at least getting y kind of out of an integrand, which I like, correct? Over here, what am I going to get? What do we always get in that situation? C, E to the, I don't have to derive that again, do I? Okay, good, thank you for C, E to the LKT. Hey, look at the answer. That's getting, do you see kind of something similar to that hanging down there in my specific solution? Totally, right? It's not quite done yet. At this point, I'm a little bit stuck because what am I trying to solve for? Y. If it were only a heart, I could break it apart and disengage it from the fraction, right? So guess what? It's, yes. That's what I love about math. I would love it to be a fart. I would love it to be a heart. Sorry. I would love for it to be a heart so I can break it apart. Totally legal in math. You're totally allowed to flip this thing over. But whatever you do to one side, you must do to the other. And what math operation flips it over? To the negative 1 power. Exactly. I'm going to repeat that. And there's other ways to solve this, but I saw somebody say flip it over, so I'm like, okay, I'll flip it over. And I can do that. And I'm going to repeat what I said. What math operation allows you to flip it over? To the negative 1 power. So I have to do this guy over here to the negative 1 power, and I get this. Somebody last hour said, but the t can never be negative. Is that true? The t can never be negative? That's actually true. Well, I suppose you could go back in time, but we're not really looking for that. But I think that's why on the screenshot of the solution, you'll see this, just to show that the time really isn't what's negative. I'd counter with the L isn't really what's negative either. What's probably negative? Yes. I did. I'm getting sloppy. There it is, e to the negative LKT. Now, I can disengage this fraction and write it or separate it. L over y minus 1 equals c e to the negative LKT. I'm not going to put it in parentheses. I'm so close. Remember, my goal is to figure out what y is, where y represents the amount present at any time. I have L over y is equal to, I'm going to add 1. Hello, denominator of the solution in the yellow box. Correct? Now what? You could picture multiplying by y and bringing it over here, and then dividing, or it doesn't really matter. You could do cross multiplying, you could flip, but either way, your y is going to be L over 1 plus C e to the negative LKT, exactly what's in this box. All right, do you need to memorize that? I doubt it. I don't. I think if you need to use it, it'll be given to you. I've only found 2 where there's logistics growth ever even in an FRQ, and a model was given to you. So you wouldn't need to memorize it. Cross this off because it's not going to be helpful. I used to do this, but there's too many things, tricks of the trade kids are trying to memorize, and that one isn't one I want you to do. So how could you remember it just in case? So I was talking about lice growing on her head for a specific reason. It is like lice, and if you think of lice minus licked, it gets you the model. Watch. Lice, right? Minus, and the cow's licking his nose, licked. So it really would. Is that helpful? Probably not. They'll probably give you the model. Some people's models are different. Again, some will have this. Again, this is variations. Some books might call that M for maximum. The one I showed you at the beginning of the hour called the constant of integration B And I've also seen books that lump this together as its own constant. Is that legal? Yeah, and they'll call that maybe K or something else. So you have to be very sure that you don't care what the variables are called, you just know what they mean. All right, so having said that, now the most important part of the curve. So this is what I've told you already. All right, that the rate of change up here, let's go write this down. The rate of change, see if you can write it. For exponential, it's just ky, directly proportional to the amount present. See if you can just, you have it down right now. The rate of change is directly proportional to what? The amount there and what's left. Does it spell Kylie? Yes, with my variables, right? Now, up here, let's look at the graph again. This point right here, I want you to label it as t, comma, the value at t. How much is there at time t? Right at this spot right here. What's true about that spot on the graph? What's happening right there? Yeah, concavity change mathematically. That's going to be important for the proof of what I do. What's happening in terms of the whatever it is that's growing? It's growing at the fastest right there. That's actually real worldwide what we like to find. This is where dy dt, the rate of change, is at a max. So when it asks you about how much is there when it's at a maximum, they're asking you about this point. Now let's suppose this was up at 500 for the carrying capacity, and let's just do a visual. If that's 500, what does it look like this is? 250. And it actually is, and I could just tell you that. I could tell you the maximum growth rate is achieved at half the carrying capacity, and would you then be able to do it right? True, you would, right? But first of all, it should make sense to you why. Back to the lice example or the rumor example. Until half the population knows it, that rate at which the rumor spreading is going to grow, correct? But once I reach the halfway point, then I'm at that tipping where just as many have heard it as haven't heard it, and then it starts to slow down. So it should make sense why that halfway point, like in common sense, is where the rate of change is the greatest. And somebody in my last hour said, is it always at half of it? And I said, yes. Is that a proof? That's just you taking me at face value. It has to do with what you said, right? So let's go, I got to prove it, okay? I could just tell you, guess what? Choose half the carrying capacity, and here's what they're going to have on the AP exam if they have it at all. Some moose population has a logistical growth curve following this model. 1 plus, let's suppose C was 5, e to the, let's say, is negative 3t. So a moose population is growing according to the logistical model blank. Sometimes they'll say, what's the carrying capacity? And what do you say? 1,000. That's not deep thought. Or they'll say, how many moose were there when it was growing at its fastest? And you'll say, 500. That's not deep thought, right? So, and will there be some of those questions? Yes. But there'll be some deeper ones too. So it says, what does it seem like the population is when it's growing at its fastest? If it really appears to be half the carrying capacity, and it is. But I'm going to use the calculus of it, what Sammy said, to prove it. Because you said that's where the concavity changes, correct? And we call that an inflection point, right? And what math happens at an inflection point? Second derivative changes sign. I can actually assume it changes zero because I can see the graph. I know that there's one concavity change in there. So it's going to have to equal 0. Do I know how to take a second derivative? Yes, but man, when I have variable soup, it's going to get a little tricky. So let's write down the first derivative. It's Kylie, K, Y, L minus Y. Think about when you take derivatives. Do we prefer the product rule or the power rule? I like power, and I'm going to avoid it. So before I even take the second derivative, I am going to write this as KYL minus KY squared. And again, without any numbers, you've got to really keep in mind who the variable of change is, Y, and what ones are constants, K and L. Okay, now I'm going to take this second derivative. Some people last hour went, oh, because when I wrote it formally, I guess I hit upon something I never really discussed last year that apparently some of them had been wondering. This is the second derivative, right? It's the derivative with respect to time of the first derivative. That's why we write it like this, because the two d's and then the dt squared. When you write second derivative, are you always confused as to whether it's dy squared or d squared x and all that? They were nodding too, and that never dawned on me last year that might have been a where do the twos go? So I said, I'll write dy dx, and you are taking the derivative of it with respect to x. So how is the top written? D squared y over dx. They're not actually squared, it's notation, but there's two d's, so d2. I don't know. They were like, oh, I'm like, I guess I neglected to tell you that last year. Note to self, right? When we get to that in Calc 1, explain to them why it's the notation the way it is. All right, so over here, this is my second derivative. So this is my d squared y over dt squared. Now, be careful. Who's the variable up here? Okay, so that's a constant. If I am taking the derivative of 5y, what's its derivative? 5. dy dt. Yes, so 5, but not 5. So this will be KL times dy dt. And again, if you don't get it, you just nod and smile. These derivations are like, I guess in terms of like a educational speak, they are enrichments. All right, the next one up. If you were taking the derivative last year of 5y squared, what would you call it? 10y dy dt. Exactly. So this is going to be minus 2ky dy dt. Now, I want to know where it's 0, so I'll replace this with a 0. What cancels or factors out? Dy dt. Remember last year when we do the ladders and we'd get like 2x dx dt, it was 2, but the 2's just go. Same here. I could factor out a dy dt and divide by it, so even if I'd forgotten it, I was okay. Maybe I'll even write the rest down. Now what do you notice is in both of them? Okay, I could have crossed that off also. Can I just divide everything through by k? And I'd get 0 equals L minus 2y. I mean, I could factor it and do that, but all right. What am I trying to figure out? What the population is when its growth rate is at a maximum. Well, solve this for y, and what do you get? L over 2. So it is always the case that for logistics growth, the amount present when its growth is the greatest is a half of the carrying capacity. Whew, right? So I just gave you a whole ton of info. I want you to suck out the key things and put them on that yellow sheet. So this is where you can write yellow. There's some stuff I want to solidify before we go do some examples. And I told you, don't be variable dependent and don't be model dependent. Understand the situation. So first of all, 100% sure you know what the graph looks like and how to interpret it. I was doing such difficult math that my smartboard's slowing down. All right, so logistic curve starts somewhere, grows fast, tapers off. And I'm going to repeat a lot of what I just said. This spot that it never gets beyond, this horizontal asymptote, this limit as I approach infinity is called the carrying capacity. It will not be asked for it explicitly. They will not usually say what is the carrying capacity. What did I say they're going to call it? And that's why I chose to call it L. A limit. It'll be written like this. This up here, the L is equal to the limit. Make sure you know the limit of what as what. The limit as t approaches infinity of what? Depends on the function. I've been calling mine generically time and some generic function y. So I will call mine y of t. Here's the next question. Can I come in from above my carrying capacity? And if so, what does it look like? And the answer to that is yes. And we're trying to think of an example. But if you come in from above your carrying capacity, you will try to reach it quickly at first. So it's going to come in and go like that. Last hour they said something about Kretschmer's fish tank. Is there a fish tank in that room? And they said it'd be like pouring, I said it's like putting way too many things in an environment that can't support it. In my mind, sadly, I kind of think of the trains used to export the Jews in the Holocaust, like they put too many in there for what that little ecosystem can support for life, and so it just you settle at your carrying capacity. They said Creshmore's fish tank, and I had no idea what they meant, but there must be a tank that's got way too many fish for its carrying capacity. So what are they going to do? I mean, they're going to die off until they reach that. So there might be a question that asks you about, like, for what y values, watch this, like maybe if this was up at 200, it might say for what y values would y of t be greater than 200, and that would be, or decreasing, it might say, and that would be when I'm over 200. Well, then it's decreasing. Otherwise, it's always increasing, right? So unless I come in from over my carrying capacity, logistics growth is always doing what? Increasing, and fast and then slow. Now let's go put some other stuff about the graph. So I want you to understand the graph. That guy right there, in terms of words, this is carrying capacity, also called a limit. This is where the maximum growth rate occurs. So dy dt at a max. What is it always? How much is there at that time? Always 1/2 of the carrying capacity. If I had a 200 up there, if the question was how much fish is in the tank when it's at its maximum growth rate, you'd say 100. Technically, yeah. Yeah, it's an asymptote. So, but that leads me to something else I was going to say, because what's going to be really helpful for you in saving some time with the math, if you really understand the models and the calculus of it, some of the questions you're going to look at and go, oh, I know it's C, I don't need to do any work. And one thing that's going to help you is not only seeing that this is a limit, but when you're thinking of tangent lines and the rates of change, what's the rate of change approaching? As I get closer and closer to my carrying capacity, what's my dy dt approaching? That's going to be super helpful for you in taking shortcuts. And they're not shortcuts, they're deep cuts. It means you understand it so much you don't have to show all the work. So I would also go over here and write dy dt up at the carrying capacity is approaching 0. That's super helpful. You'll see why when I get to the multiple choice. That's going to allow you to not have to care what the variables are, not have to morph it into a model you know. Your limit of your rate of change approaches 0 at its carrying capacity as it approaches it. So that's the graphical of it. Next up, draw a line. The models of it. What does the Diffie-Q look like? It looks like, from what I gave you, I said, because I gave you it in its easiest to remember form. What did I say it is? K y times L minus y. Now that can be morphed into other things. So sometimes you're going to see it written like this. You'll see a 1 here minus y over L. What did I actually do with this? Divide it by what? L. Is that legal? True or false? Yes, but if I divide something by L, I better multiply it by L, right? So they'll multiply it by L and just have like a different, I'm going to call it K sub 2, but sometimes you'll see it as this. These two models are the same. In this model, what's the carrying capacity? L, right? In this model, what's the carrying capacity? L, but here's why. When you put an L in here, what do you get for the derivatives of both of them? 0. So just let that help you, and then you won't have to worry about going from this form to this form. If you're totally confused by that, I'm going to throw up an example really quick from in your notes. It's right, there's a multiple choice one that I'm going to tell you right now because I get the models and what it's asking. So in 2003, this was their number 21, didn't have great statistics, not because the math is hard, but because kids didn't understand the model or the notation. So this is moose in a national park, and this is the rate of growth of the moose, and then it says find this. What are they telling you to find? Carrying capacity. I wouldn't mess with the model. I would just say it occurs when the rate of change is 0. And what value for M would make this 0? Either 0, which isn't helpful, because I can't have 0 moose, or I wouldn't have moose, right? So what's M? Was that hard? No, because I understand the model. What do you think a lot of kids don't understand? First of all, what are they asking me for? What's this limit? They're asking you for a carrying capacity. How do I find it? It's not in the model my teacher taught me, because you need to understand that the derivative is going to approach zero. So no matter what model they give you, it shouldn't matter, right? And no matter what variables they give you, yeah, it's an M, and I know Kylie. Well, yeah, then you're screwed, because you need to be able to morph it. Watch the next one. Why is the answer 10,000 without me doing any work? I have a circled answer. I screenshot it, so it's off as somebody's already done something. Why is that 10,000? Because that's where the derivative equals 0. And the carrying capacity is where the derivative equals 0. So this is, all I do is pretend I'm setting it equal to 0. And the model that or the form and the variables, even if it's even more complicated. Again, when I screenshot these, I have a whole bunch I can pick. What ones do I choose? The weirdos. I didn't give you the ones where it says, what's the carrying capacity? 300 over 1 plus blah, blah, and you just circle 300. I didn't pick the ones that say, what's the maximum what is the population when it's growing the fastest, and you just take half of it, because that won't get you. I picked weird ones, but I'm giving you a way to tackle them. So go ahead and read this. You are in charge of stocking Creshmore's fish tank with the rate of population growth modeled by that. Right? There it is. It says, find this. What are they asking you to find? The start doesn't affect, it'll affect my graph, but I'll start up here at 50. I guess since it says to graph it, I'll go like that. But I know I'm going to grow fast, and then boom. You might say, that's not in the Kylie form. No, and you could choose to try to put it in that form if that's what you get, but I'm going to tell you that this limit will be achieved when the derivative equals 0. So all I need to know is where a function equals 0. To figure out where a function equals 0, I factor it. I'm just going to pull a p out and go, it's 8 minus 0.02p. That has to be 0 at the carrying capacity. And I don't care about the fact that it's p's or the fact that they've messed with the format of it, because it's easy for me to figure out where this is 0, because the fish, there has to be some there. So I just solved that. Maybe I don't have a calculator. So then I have to say, okay, well then 0.02p has to equal 8. So I have to do 8 divided by 0.02. Oh no, how do I do that without a calculator? I write it as 8 over what? 2 over what? 100. Yes, which is 8 over 1 over 50, right? It's doable. The arithmetic is what's going to get us. So I'm going to go through that, because that's actually where you guys screw up. How do we multiply decimals? You're killing me, kids. What's the answer to this? 400 would be the carrying capacity. What if I piggybacked with a question that said, when the population of fish is growing at its fastest, how many are in the pond? 200, right? Half the carrying capacity. Before I do this difficult one, I want to go back before the belt. We're going to stop. That'll be the one I start with tomorrow when I have time. I want to go back to this sheet where we have your yellow sheet. All right, so we've got the models that we're not going to worry about the variables or whether they distribute this in and write it differently. If it's logistics growth, I'd write watch for where it equals 0. That's where your carrying capacity is. Next, for your model, maybe, I doubt it, you would need to know what y is, but I gave you a way to remember. I gave you a picture of a what? Lice. Lice minus licked. It'd be L over 1 plus CE, there's lice, minus licked. Do you need to memorize that? Most likely no. But if you see it in this format, where's the carrying capacity? On the top of the fraction. What is the population when it's at its maximum growth rate? Half of what's on the top of the fraction. We're done. Okay, so what are we doing tomorrow? You're going to come in. I'm going to do 2 more examples that are in word problem format, not like multiple choice. Then you're going to take a quiz on exponential growth, not this stuff. And then I'll give you your logistics growth worksheet. If you want that right now because you might be gone tomorrow,